So chapter 15, we talk about multiple integrals. And we're going to get into double integrals, triple integrals, which all have a lot of great applications. And we'll obviously get to those as well. First, we'll go and talk about the basic structure of starting with a double integral. Now, this first part of 15.1, I'm actually not going to be emphasizing too much. In fact, you shouldn't see too much of 15.1 on a test, at least the first part anyway. You'll see a little bit of 15.1 on the test, but the first part of 15.1 is very clunky because it involves Riemann sums. So before I get into Riemann sums, let's just go ahead and talk about definite integrals back when you had Calculus 1. And as we review definite integrals, I want to go ahead and take a look, and this is from the book. If you recall, we took what was called a Riemann sum, which is, is this summation notation right here. And if you recall, it's basically the height of the rectangle times the width of the rectangle, and we basically just added up a bunch of rectangles, and usually we get some sort of estimation. However, I want to point out though that we obviously don't want a Riemann sum. Eventually we want a definite integral, which basically takes a limit as n approaches infinity, essentially packs in infinitely many triangles into one small location, and this estimation slowly becomes an exact amount. And that's kind of the same idea that we're going to do with double integrals. The difference here, though, is that double integrals are going to be a little bit more complicated. Now I'm going to go ahead and show you guys Riemann sums. Now again, I told you that 15.1 won't be totally emphasized on the test. There will be definitely some aspects to it that you will need to understand. But definitely I will not emphasize Riemann sums because check this out. Volumes and double integrals. Let's go ahead and transfer that idea of a Riemann sum over to double integrals. Well, in Calculus 1, a Riemann sum consisted of you adding increasingly numbers of rectangles. Well, in this case, we're going to use a similar process to define a double integral, but instead of being over some sort of interval, we're going to be over some sort of plane. So consider a continuous function such that your function is greater than or equal to 0. Basically, it's like a beach canopy hovering over the ground. And it's hovering, in this case, over the xy plane. And let's say we're trying to find the volume that lies between the surface and the ground. So the xy plane here is the ground. We're going to begin by partitioning the rectangular grid over the region R. Let's go and take a look at a picture here. So notice how we have F here is above the ground, and here's the ground down here. What if you were asked to find the volume of this solid that's hovering over this floor here? Well, what's going to happen is we're going to partition it, but notice what happens is instead of being rectangles, we're partitioning the ground into rectangular grids, which create rectangular prisms. And if you recall, in geometry, obviously, the volume of a rectangular prism is length times width times height. And so essentially, we'll be doing the same thing here with the Riemann sum, basically length times width times height, the height being the height of the actual surface itself. And obviously, that looks pretty crazy, and you could probably already see why putting a problem like this on a test might not be very efficient. So I will have some elements of it on the test, but again, like I said earlier, it will not be emphasized. Now, I'm going to go very quickly through this. Essentially, it's dividing the floor, the region on the floor, into m subintervals and n subintervals, where we have not only delta x, but we also have a delta y involved. Now, if you recall back in Calculus 1, delta x eventually becomes dx when you are integrating, and you can kind of imagine that delta y becomes dy when we eventually integrate. And so we're going to go ahead and form these subrectangles. Okay, again, each with area delta x times delta y. And then we're going to continue for all the rectangles and add up the volume of every single rectangular prism. And that's going to give us just an approximation. So obviously, I don't want an approximation. I want an exact volume. Eventually, we'll get there. But for now, we are just looking at approximations. Now, clearly, the approximation becomes better as m and n get larger, meaning another way to say it is, as we pack more and more rectangular prisms into that region, just like a Riemann sum from Calculus 1. So if I simply just slap a limit in front of the summation notation, and as m goes to infinity, and as n also goes to infinity, you get a more accurate, in fact, you get an exact volume. And then obviously, if we just go ahead and take that limit, as m and n go to infinity, that leads us to what is known as the double definite integral. Obviously, provided the limit exists. And then, of course, it would be nice, again, if we're doing Riemann sums, it would be nice to choose convenient subintervals. And, you know, make this thing convenient for ourselves. Now, you might wonder, well, why are you repeating yourself here from here to here? It's not quite a repetition. If you notice that this has an asterisk and these don't, the asterisk means that you can actually really place your subintervals wherever you want. According to Bernard Riemann, the smaller the subintervals get, it doesn't actually really matter where you place your points, whether you use midpoints, left points, right points, it doesn't really matter. But down here, it's where you actually get to choose yourself where you want your points to be. So it's really not quite a repetition, even though it seems like it. And here's, of course, the definition from the book itself. But why don't we go ahead and do an example? Now, again, the following couple examples, I'm not going to emphasize on the test. I might offer a portion of the test dedicated to the Riemann sum. But let's just go ahead and get through a few just to make light of what the Riemann sum does for us. So we're going to do a Riemann sum here. Essentially, we're going to go ahead and take a look here. We're going to go ahead and let our subintervals be convenient. Notice that we allow our subintervals to equal to 2 for both m and n. And we're going to go ahead and choose the upper left corner. You'll see what I mean in a moment. By taking sample points of each sub-rectangle. Now, you guys all see this x minus 3y squared here. That's going to be my f. That's going to be my function f. And then we have this big rectangle here. I'm going to go ahead and draw a picture, provide for you a picture here. So we see the picture here. As you can see, this rectangle is doing exactly what the problem calls for. X is going from 0 to 2. And y is going from 1 to 2. So what we're going to do is we're going to go ahead and take this region here. And now this region is actually what's on the floor. So this is our shadow. So above this, it's kind of hard to see, but this is the bird's eye view of the region we're going to go ahead and integrate. Again, we're not looking at the exact integration. We're actually doing an estimation. So if we take a look at the upper left corner of each of these boxes, okay, so the upper left corner would be these little corners right here. So here the arrow is pointing at this upper left corner. Here's the next upper left corner. Here's another upper left corner. Here's another upper left corner. So I'm going to go ahead and just kind of reveal the point of this as we go. So essentially, we're going to take the Riemann sum as I starts at 1, goes to 2, j starts at 1, goes to 2, and essentially we get this. What we're going to do is we're going to evaluate f, now again, f being x minus 3y squared. Okay, so we're basically going to go ahead and plug in each one of these points into this function that we're trying to integrate. Okay, and then multiply it by the area of each of these rectangles. Now, as I reveal each one of those, negative 27 over 4 is exactly this. It's this first point right here. So 0, 3/2. Well, where is 0, 3/2? 0, 3/2 is this first rectangle here, rectangle 1, 1. You'll notice that the upper left corner of this rectangle is the point 0, 3 over 2, which is why I have the point 0, 3 over 2 here. And then what's this 1/2 all about? Well, okay, again, the 1/2 is you take the area of each rectangle. So the area of this rectangle here is length times, base times height. So the base is 1, the height is a height of 1/2. So 1 times 1/2 is just that, 1/2. And then moving on to the next term, 0, 2. Well, where's that point? The point 0, 2 is up here. As we can see, this point is the upper left-hand corner of this rectangle. Okay, and so again, you take the point 0, 2. We're going to plug it into this function here. When you plug it into this function here, x is 0. That's going to make that 0. Y is 2. 2 squared is 4. 4 times negative 3 is just that, negative 12. So that's where the negative 12 comes from. And again, times 1/2. And then here, this comes from the point 1, 3/2. Again, you plug in 1, 3/2, you get 1 minus, and then 3/2 here gives me 27 over 4. 1 minus 27 over 4, again, times 1/2. And finally, with this last point over here, this is the point 1, 2. You go right 1, up 2. That's this upper left-hand corner. Is going to give me 1 minus 12. That's negative 11, obviously, if you plug it in here. And again, times 1/2. Now, you'll notice all the terms have a factor of 1/2. So you actually don't have to multiply every single term by 1/2. You can actually just go ahead and factor out a 1/2, and then just add up all these heights, and then be done with it. And you should end up with negative 17.75. So that's for an upper left corner. How about the upper right corner? Here's that picture again. So my upper right corner, you can kind of guess. In fact, before I reveal the answers to that, the upper right-hand corner of each of these boxes, just go ahead and guess what they are, the coordinates of those. Obviously, 2, 2 is one of them. 2, 2 is the upper right-hand corner of this box up here. So before maybe you can pause here and just go ahead and guess what would be the upper right-hand corner of the other boxes. And hopefully this makes sense. Again, I factored out that 1/2 because all of them will be multiplied by the area of 1/2. My first upper right-hand box is 1, 3/2. That goes right 1, up 3/2. It's the upper right-hand corner of R11. This next one is 1, 2, which is right 1, up 2. This is the second upper right-hand corner of R12, and so on and so forth. Again, each one of these points you plug into the function here given, x minus 3y squared. And then you simply just add them up, multiply by 1/2. In this case, we get negative 15.75. Notice it's a different number as the previous answer. Again, these are approximations, just like in Calculus 1. Different types of approximations of Riemann sums will give you different results many times. There's lower left corner, there's lower right corner. So I'm kind of speeding through this here. And there's also midpoints. So why don't we go and try one where there's midpoints. So this is just like example 1. Let's say we wanted to find the volume or estimate the volume that lies above the rectangle on the floor, 0, 2, 0, 2, but below the elliptic paraboloid, and we're going to use midpoints. So once again, that is our region that we are discussing and that we're determining is going to be our subintervals. Z is our elliptic paraboloid. That's this guy. This is going to be our function f. So the point is that every single one of these rectangles has an area of 1. So notice how I factored the 1 out here. Okay? And then all you're doing is adding up the heights of their respective midpoints. Well, this first midpoint comes from this square right here. Well, obviously, if I go to the right half and up half, that gives me the midpoint of this rectangle. That's how you get 1/2, 1/2. And I think going around this whole thing, you can tell where all these other ones come from. For example, the second one, if I go right 1/2, up 3/2. That's going to give me my midpoint here. And you can kind of see where the other two come from. And you go ahead and take each one of these points, you plug them into this. Okay, that's going to give us that. And the answer in this case is 49. Now still, this is an approximation. Even though we got a nice number this time, a nice whole number, it's still an approximation. The actual answer is probably a little more complicated than that, most likely. Not always, but in this case, we at least can safely say it is an approximation. Now let's take a look at some properties of double integrals. Now here's the thing. I'm not going to emphasize Riemann sums on your exams, but I do want you to do the homework for it, obviously. But the properties of double integrals are quite basic. They're kind of similar to what we've seen before. Now this is from the book, so I'm just going to go through this very quickly. For example, if you think back to Calculus 1, the integration of a sum is the same as the sum of integrations. So it's very similar. It's very similar to the linearity of the integral. Also, constants. I think we all know this. You can factor out constants if that's more convenient for you. And then finally, if the volume, or excuse me, if the height of a surface is greater than the height of another surface, then obviously the volume of the higher surface is going to be also greater than the volume of the lower surface. So again, think back to Calc 1. Now, Calc 1, when we first learned about integrals, we were looking for the area under the curve, correct? Well, now with double integrals, we are looking at the volume under a surface. So now let's go ahead and take a look at what are known as iterated integrals. And what we're going to see is we're going to kind of break up a typical double integral and to show you what exactly is expected of you when you integrate a double integral. Now, note the following integration and look at the following notation. Notice that in this integral here, this integral is actually asking us to integrate with respect to y, as I'm sure you can see. So much like partial derivatives, right? Whenever you are taking the partial derivative with respect to y, we're going to hold x fixed, right? Or as a constant. So it's the same thing here. So just like partial differentiation, with partial integration, you're going to go ahead and integrate this thing and treat x as if it's a constant, at least for now. So again, if you are pretty good at partial differentiation, then you're going to be pretty good at partial integration because, again, you'll be holding the x fixed or constant. And this is known as partial integration. Now, something I want to point out here also is that if I am integrating from c to d, then ultimately out of the y we get some sort of actual constant, but yet you still have an x involved in the function. Therefore, this is actually a function of x. Even though there's a dy here, you are integrating dy from c to d. So that means y eventually is going to be kind of omitted from this ultimate expression, and it's going to become a function of x eventually. Okay, but then of course, once you have that accomplished, you'll notice that I'm going to go ahead and start building the double integral here. Look inside the bracket. The bracket inside here is what we talked about in the previous slide. But then whatever comes out of this is now going to be integrated with respect to x afterward. So it's just like order of operations. Order of operations, we always do what's inside the parentheses first, right? So we take care of all this inside stuff. Once we take care of all this inside stuff, we now can go ahead and integrate with respect to x. Okay, and the right side of this above integral is called an iterated integral. So in other words, you're kind of like taking this thing and all you're simply doing is integrating first with respect to y, then integrating with respect to x. Now, does it have to be done this way? Well, the answer is no. In fact, I'm just going to go ahead and show you the next slide. This next slide is from the book. Notice that in this next slide, we're first integrating with respect to x, then we're integrating with respect to y. But it depends on what your situation is. And by the way, I'll be explaining which one you're supposed to do first or which one you should do first. Really, most times it doesn't matter, but sometimes it is a matter of simplicity. But the point is, in either case, you are working from the inside out. So I'm going to go ahead and do an example here. So notice here in this particular problem that we want to work from the inside out, right? So what that means is, if you all see that I have a dy here, yes? Well, because I have a dy here, that means that this 0 to 1 are my y values because it's closer to each other. These are the inside values here. So again, the dy is here. That's physically placed here, and this is very important. Because the dy is placed here, that means whatever integral is closest to it will be the y values. And then you'll notice that outside of that is dx. That means whatever integral is outside is going to be our x values. So that's a very important point, especially when we get to triple integrals. So what I want you to notice here is that what we're first going to do is we're first going to integrate this thing with respect to y. And notice that if you integrate this with respect to y, it's just simply the power rule, isn't it? So we go ahead and take this y cubed, and how do you do the power rule there? Well, it's again, you raise it to the higher power, 4, and then we divide it by 4. And notice how the x cubed was held constant. You see how we go from x cubed to x cubed here? So it's all, it's basically held constant for now. And then, of course, over here, y squared becomes y cubed. And then we went ahead and divided by 3. You might notice there's no divided by 3 here because it canceled out with this factor of 3 here. And just like fundamental theorem of calculus part 2, we go ahead and evaluate from 0 to 1. Okay? Obviously, the 0 is going to cancel out both these terms. So we only really need to consider the 1, which is going to give us this result right here. 1/4 x cubed plus x. Now this becomes a very, very simple calculus 1 integration, which becomes this, integrating from -1 to 1, and then evaluating and ultimately get 0 for this particular problem. Now, if we look at the book, there's something known as Fubini's theorem, which states that as long as you have a defined rectangular region, it doesn't necessarily have to be rectangular, but if it is continuous on this rectangle here, then it actually doesn't matter what order we integrate with. So notice in that last problem, we started with dy, and then we did dx later, right? Well, if I would have done dx first, then dy, then you'll still get the same answer. We'll see in a moment. Now, here's the thing. There's a warning down here at the bottom. You are welcome to integrate in either order if you have defined limits for both x and y. You're allowed to do that. However, the problem though is that sometimes one integration might be more difficult than another. So you want to be careful. You want to be keeping things safe, and secure with your integrations. So try to find the one that's more simple. Now in this particular case, if you notice, I went ahead and took the same exact problem. Yes? Okay, here's the same exact problem I gave. And now I'm going to go ahead and we're going to integrate it, but we're going to switch the integration procedure. So notice how dy, I changed it to dx, and dx changes to dy. And we'll go through the same process. So first I'm going to go ahead and integrate this thing with respect to x. That means this is going to become 1/4 x to the 4th. This is going to become 1/2 x squared. Right here. We integrate from 1 to -1. That already is going to give me a 0 right away. And then we all know from calculus 1, the integral from the integral of anything of 0 is going to be 0. All right, here's another example. This one's a little bit different, but it's going to start off the same way. So I really want to explain to you that you want to make sure that you have your limits in the right places. So for example, we take a look at this one. You'll notice that this one says x sine y dA. Now dA is just simply a differential about the area. And this actually just simply means dx dy or dy dx. It can mean either one. Again, it doesn't matter if we integrate with respect to x or y if we're given defined limits for both x and y. Notice here we have defined limits for x and a defined limit for y. So this could be dx dy or dy dx. So let's go ahead and let's just do dx dy. Since the first one we did dy first, let's go ahead and do dx first. And you'll notice again that dx is here, right? And the integral closest to it are the actual values for x. So if you were to put 0 and pi over 6 here, that would be incorrect. So the innermost integral with the innermost differential must match. And notice how the outer integral with the outer differential also match. Notice how the y values are here, and so the dy is here. Now, hopefully you understand that. That is important, and that needs to be understood before we get to triple integrals. But what also is very important is that you'll notice that this problem is actually kind of unique. This one's unique because you'll notice that what we have here is a product of x, of something in terms of x, and something in terms of y. So because of that, we actually are able to do something kind of special here. So because of this, we are actually able to go ahead and separate them actually. This is totally allowed only if you have a product of something that's explicitly x times something that's explicitly y. So as you can see here, I was able to separate these, and this is the only time where you're able to do this. If you cannot separate them, then they must be done in the way that was shown in the previous example. And I'll show you more that are like that momentarily. But this is nice because now this becomes two calculus 1 integrals in one problem here. So we go ahead and solve for it, and you should end up with this as your answer. I don't think this one's that difficult. So I'm going to go ahead and move on to another example, same kind of idea. Now again, we have defined limits for x and y. And once again, notice that I have a product of something explicitly x times something explicitly y. So as you may already understand or guess, you are going to be able to split these up. But again, before I do, let's go ahead and make sure we understand the order of things here. Notice that the dy is here, and therefore my y values are here. And my dx is on the outside here, so that means my integral for x is also on the outside. Again, 0 to 2 are my x values. Again, very important. As I mentioned before, though, we have separable factors of something explicitly x times something explicitly y. So again, you are able to split this up into two different integrals. And once again, it becomes a very simple calculus 1 integration problem. So I just went right to it, gave you the antiderivative. I will show the steps for the antiderivatives eventually, but just know that some of the calculus 1 methods I don't show. But just so you guys know that this part right here that was done, I basically did it by parts from here to here. Okay, so hopefully that's understandable for you. And then we obviously get this, and the answer is 2. So the last two examples were nice because we were able to separate them and basically just calculate the product of two single integrals. Now for this problem, you'll notice that we actually cannot separate. So in the last couple examples, we were able to take the product of something explicitly x times the product of something, times something explicitly y, and integrate two single integrals. Here, we will not be able to do that. So here we actually do have to integrate according to the first double integral I showed, where you go from the inside out. Now again, it doesn't really matter if you do your x first or your y first when you are given very well defined limits here. Now when it's presented like this, we can go ahead and it's fair to assume that the first set of brackets are my x values and the second set of brackets are my y values. So let's go ahead and begin with this. Now I'm going to go ahead and go dx first, then dy. And again, notice that dx is here and my limit from 1 to 2 is here. And if on a test, if you were to present this to me where dx was here but you put your y values here, I would mark you down for that. So please make sure that you are taking note of this. It's very important, especially when we get to triple integrals. So this is dx is going to be first, which means my limits with respect to x will also be first as well. And also notice, guys, that my dy is on the outside, therefore the dy is going to correspond to my integral with the y limits on the outside as well. Now integrating this is pretty simple. It's 1 over some argument, and whenever you actually integrate 1 over some argument, it's going to be natural log of that argument divided by the chain rule and all that. But in this case, we don't need to worry about that because it's a pretty simple argument here. But this should be fairly straightforward, I believe. And so we go ahead and take a look at this, and we're going to go ahead and integrate this with respect to x, and then fundamental theorem of calculus part 2 will have us evaluate this from 1 to 2, which gives us this. And now it becomes a function. Now, if you recall back to calculus 1 and even calculus 2, the integration of natural log is going to be either a table or integration by parts. I actually don't mind if you use a table or integration by parts. So just so you know, for any exam, if you ever use a table, please indicate to me that you did. And I typically will accept it unless I indicate otherwise. But if you don't remember or don't have it memorized, you can just do this term by parts, which gives you this. So you'll notice you have the argument times natural log of the argument minus the argument. That's what the table is going to tell you. So I have the argument of 2 plus y. So it's going to be, again, 2 plus y, the argument, times the natural log of the argument minus the argument. That's the formula for the table. Same thing happens here. That way you don't have to integrate by parts. And then after you do all the work, you should ultimately end up with natural log of 27 over 16. Now this is my very simplified, nice, and clean answer. Okay, my simplified, nice, and clean answer. So as long as yours is numerically equivalent, it's probably fine. All right, let's go ahead and finish off this lesson with what are known as average values. Average values are very similar to what we learned back in Calculus 1 when you talked about the average value of a single integral. Now, what is the average value? Well, the average value is going to be essentially the average height of the function from a to b. So essentially, kind of recall like you have a function, let's say it just kind of goes up and down, right? From left to right. What would be the average value of all these peaks and valleys, right? The average value would probably be something like this, kind of a bad drawing, but it basically gave you the average height of where would this be from A to B. And that's essentially what we're going to do with volumes as well. The average value of a double integral is kind of similar in that instead of being the average height of a function, we are going to look at the average height, but in a slightly different way. Now, both of these are dealing with height, the height of the function itself. Now here, it's a function of one variable. Here, we're talking about a surface down here for a double integral. So let me show you a picture and show you what I mean. So as you can see, I have all these peaks and valleys, right? And it's like kind of like some mountaintops coming out of an ocean here, right? Well, the ocean here represents what the average water level is going to represent the average height of these peaks and valleys. So the valleys are obviously pulling the water level lower, but the peaks here, the mountaintops, are pulling the water level higher. And the point I'm trying to say is that the volume of this water here should be the exact same volume of all this mountaintops that we're looking at here. So it's essentially the same idea, but again, remember we are calculating height, not volume in this case. So whenever you're asked to find an average value, you're asked to find height, not area, not volume. So I say let's just get right into an example. So what if I wanted to find the average value of this surface over this rectangle? Well, my area of the rectangle, I want to start there because again, if I go back to my formula, it's 1 divided by the area of the rectangle times the double integral. So I go ahead and find the area of the rectangle, which is going to be just simply the length of this interval, which is 0 to pi over 2, which is pi over 2, times the length of this interval, which is 1, 0 to 1, which gives me just pi over 2 in this case. And let's go ahead and write that formula out again. Okay, now it's simply going to be 1 divided by pi over 2 times the double integral of my function on this rectangle. And remember, dA could be one of two things. It could be either dx or dy. First, it doesn't matter to me. So again, it could be dx dy or dy dx. Just make sure you have your limits in the right spots. Now, I'm going to go ahead and start with dy this time. So it's 1 over pi over 2. Notice that my innermost integral corresponds to dy, which makes sense, right? And my outermost integral corresponds with dx, which corresponds here as well, nicely. And once again, we are going to integrate from the inside out. Now, this is another practice integral. This is great. We cannot separate these two because it's not, this is explicitly x here, but this is not explicitly x here. It has x and y. So we actually do have to integrate from the inside out. Now notice, you actually can integrate with respect to x first, but there's a very specific reason why I'm integrating with respect to y first. Notice that if I integrate with respect to y first, I end up with this. You get it in one step because we all know the antiderivative of a sine is cosine xy, but then you have to divide by the chain rule factor of, in this case, x, which is going to cancel with this x, leaving me with just simply negative cosine xy. So to me, doing dy first is an easier integral to do because if you do it the other way, if you do dx first, you're going to have to integrate by parts, which is fine. But either way, you end up getting this. In this case, you end up integrating with respect to y now, x now, which is pretty basic and easy, which gives us this, which equals to 1 minus 2 over pi. Now, what I recommend to you, now I know you probably don't want to do this. Most students only want to do the easier method. Please try yourself right now. In fact, I would pause this video right now. And please try to integrate this thing. And again, don't forget to multiply by this factor of 2 over pi. But please try this integral again. But this time, switch the dx and the dy. You should still get the same ultimate answer when it's all said and done. And trust me, if you actually practice that, and please hear me on this, if you actually go ahead and switch the dx and the dy and actually integrate with respect to x first, then with respect to y, I'm telling you, the practice is going to pay off huge dividends. So please follow my lead, trust me on this. Go ahead and pause this video right now and try doing it the other way and get the same answer. And if you're not getting the same answer, reach out to me, email me, let me know, take a picture of your work, send it to me, and I can give you feedback. Now lastly, I don't really want to emphasize this too much, but the book does give you other properties that you should be aware of. Now again, like I said here's one property. Again, I want to emphasize this and then say that if you are able to separate the two integrals, please do so. And we've already seen a couple examples of this, but the reason why I want to show you again is because this is your first line of defense. Before you actually even go ahead and integrate from the inside out, check to see if it can be separated. Because if it can be separated, you are saving yourself a ton of time and possibly a lot of work. So I just wanted to show this again just to emphasize that fact. Let's go ahead and take a look at one last example for this lesson and then we'll conclude. It will also be wise to determine if you have some sort of symmetry going on. Sometimes symmetry really helps you out and causes you to work less and have simpler conclusions. So for example, we take a look at this one. Now obviously we can separate it a bit. Now we can obviously, since this is separated by plus signs, remember that the integration of a sum is the same as the sum of integrals. So I'm going to go ahead and separate it that way as well, for sure. So let's start with that. So you are allowed to do this, even though you have x and y involved. You are still allowed to do this. Now, one thing I want to point out here is that whenever you have the double integral of 1 dA, keep in mind that it's almost like the fundamental theorem of calculus 1. This double integral will kind of like cancel out, I guess is the word for it, this differential here. And you actually end up with just A, the actual area of the rectangle. You're going to see this pop up a lot. So before I get to these other two, take a look at this. Anytime you have a double integral of 1, all you have to do is find the area of the rectangle of your limits that were given to you, and that's all you have to do. Okay? So obviously, these two I'll get to in a moment. Okay? So I'll just go ahead and repeat myself. So again, the double integral of 1 dA is just simply the area of the rectangle that you're dealing with here. Obviously, the length of this first interval is 2 pi. Going from negative pi to positive pi is 2 pi. And going from negative pi to positive pi again is 2 pi. Okay? So again, negative pi to positive pi is 2 pi here. Negative pi to positive pi is 2 pi here. Okay? But notice that sine is odd, right? So you'll notice since sine is odd, then whenever you take the integral of something symmetrical of sine, well, that's going to become 0. Anything symmetrical about sine is going to be 0. Therefore, this whole entire double integral simply becomes 4 pi squared, that's from the 2 pi times 2 pi, plus 0 plus 0, you end up with just 4 pi squared. So this big old complicated looking double integral, all you're simply doing is multiplying by the length and width of the rectangle and you're done. So look at all this writing. See all these notes here? You're probably writing a lot of this down. If you could recognize that that's the case, you can go from the question almost directly to the answer right away, and I'm totally okay with that if you recognize symmetry. So two things to point out is, one, whenever you are taking a double integral, always look to see if it's separable. If it is, your life is going to become a little easier that way. Second, if you can notice symmetry, that's also going to clean up some stuff and make your life a little easier as well when taking double integrals. It's not going to be quite the same when it comes to triple integrals. Triple integrals add an extra layer of complexity. While there is some symmetry involved, it's not going to be quite as simple as double integrals, so be careful there. But anyway, this concludes the lesson. If you have any questions, please reach out through email or through our next Zoom meeting or through a chat somehow. And I wish you well, and also please continue on and read 15.2 as soon as you can.